Hi, I'm Ann Stinnett. I'm the math specialist for the Knox County Schools, and I'm going to bring you this week's KCS at Home for 8th grade math. We are on week 5, and week 5 is going to be a little bit like week 3. You have only one page in your packet. We're going to be doing some review problems with functions, and it will relate closely with all of the work we've been doing with our KCS at Home packets so far. We're going to be reviewing slope-intercept form, and interpreting some problems in terms of the functions that they represent with tables, graphs, and equations. This video will also air on PBS on Tuesdays at 2 o'clock. That's our math day, and you can download the packet from knoxschools.org or pick it up at your meal distribution sites on Wednesdays. Today we're going to start warming up our brain with a visual pattern. And you can see on the screen we have a series of X shapes that are growing at a constant rate. And at the bottom, you might not be able to see, it says squares in step 43 equals 173. I went ahead and organized the information in a table for myself, but if you're able to pause right now and see if you can figure out an expression for any term in this sequence or the nth term in this sequence. If you're watching live and you're unable to pause, I'm going to go over how I figured this one out, and then I'm going to give you another one at the end of the video that you can do on your own. But all of these patterns come from a website called visualpatterns.org, and there's lots of them to do if you enjoy this kind of thing and want to do some more. So let me explain how I figured this one out. One hint on all of these is if you sit down and draw them, sometimes the way that you draw the pattern gives you an idea of how the pattern works and will help you write that expression. So I noticed on this first one, it started with 5 squares. So step 1 had 5 squares, and it just looks like the pattern you would see on a die. And then when I went to do the second step, there are 9 squares, and when I drew it, I started with that original pattern of 5, and then added 1 square to each spoke of the X. I don't know if spoke is the right word, but that's what I'm going to use for me. When I went to the third term, again, I started with that initial 5, and then I added 2 squares to each spoke. So that told me that there's one thing that's constant through the patterns, at least in the way I drew them, is that they each started with 5. So when I went to write my expression, I started with 5, because I knew I was going to add that initial 5 to each one. And then I tried to figure out, well, what am I doing each time I add the squares to the spokes of the X? So in the first one, I noticed I didn't add any at all. So step 1, there were 0. Step 2, I added 1 extra square to each part of the X. And step 3, I added 2 extra squares to each part of the X. So since there are 4 diagonals to the X, I knew that I was going to be multiplying something by 4, because I had to do that to each side or each spoke of the X. Since there were 0 in step 1, and 1 extra square in step 2, and 2 extra squares in step 3, I noticed that those extra squares, each number was 1 less than the step I was on. So if I were on the nth step, I would subtract 1 to figure out 1 less, and that would give me the number of squares in each part of the pattern. So to check that, I can plug in 43 as my step number to this expression that I've created. 43 minus 1 is 42. 42 times 4 plus 5 more is 173, so I know that I have done that one correctly. This week's activity is coming from the functions domain. Again, it's closely related to proportional and non-proportional relationships and all of the work that you've been doing so far in these packets. So today's standard is number 4. We're going to construct a function to model a linear relationship between two quantities or two amounts. We're going to determine the rate of change and initial value of the function from a description of a relationship or from two xy values, including reading these from a table or from a graph. We're going to interpret the rate of change and initial value of a linear function in terms of the situation it models and in terms of its graph or a table of values. So essentially we're going to be looking at relationships between two numbers in a variety of ways and determining or interpreting them based on what those representations mean and what they tell us. So the key vocabulary here, of course, is function. A function is simply an input-output relationship that has exactly one output for each input. And you've been doing these since elementary school. I'm sure you remember input-output tables, looking for patterns in tables. Maybe you've even seen a function machine before. But essentially, the examples on this slide, in this first function, we have x values 1, 2, 3, 4, 5, 6. And the y values are just twice that every time the x value is being doubled. So if I put in 1, the function spits out 2. And then 4, 6, 8, 10, and 12. So this is a table of a function. The matching equation would be this. If my input is x, I would simply be putting this x value into the function or into the equation. Multiplying the x value by 2 would give me the output, or y, and that's constant. That's the case every single time. So every x value is going to give me only one y value. And you'll notice some patterns as the x and y values increase and decrease as well. For not a function, you'll notice this table on the right has an x value that gives us 2 and an x value that gives us 5. We cannot have two outputs for one input in a function, so this is not an example of a function. Our next term is linear relationship or linear function. We've talked about linear equations. So these relationships give us a line. And when we're looking at equations and tables, a linear relationship depends on how x and y change. If y increases at a constant rate, then the relationship is linear. And of course, what makes a straight line when we put it on a graph. So a nonlinear relationship just doesn't make a line. It might make a curve, sometimes a parabola, and different shapes in the graph. And the final one is rate of change. We've talked about unit rate, we've talked about rate of change, and it's simply a ratio that compares the amount of change in the dependent variable, or the output, the y, depends on what x does, and we compare that to the change in an independent variable, or the input x. So on a graph, when we determine rate of change, it's essentially the same thing as slope. We take the change in y and over the change in x. And then we take that ratio, and if that ratio has a change in x of 1, or the denominator, the bottom number in the ratio is 1, then we have the unit rate. And we can interpret that through the graph, looking at the rise and the run, or the equation for determining slope. So that's what we're going to be doing today, in a variety of different ways of looking at it. Before we get started today, I want to show you a resource that I'm going to be using to help us interpret our problems, and it's called Desmos. You may have used this in class. You may have never heard of it before, but you might be using it next year in your high school classes as well. So I just wanted to give you just a really quick overview of Desmos and how to use it if you decide you want to do that. So this is what the home screen looks like, desmos.com, and you simply click on Start Graphing. It's essentially an online graphing calculator. And you'll notice here I have my graph. You can see, you can pull it around, move it, zoom in and out, etc. This one's untitled because I'm just going to show you how it works. But I can add different things. I might want to add a table. So if I want to use the function from our vocabulary example, I could put in 1, 2, and I'm just entering each time. And then my y values were doubled, 2, 4, 6, 8, 10. And you might have seen on the graph now that those points are plotted on the graph. Very simple. I can click here on this green dot, and if I hold my mouse down, I have different options. I might want to connect those dots. I can change the color of the line, do whatever I want to do. I could also go in and I could put the equation for the function, y equals 2x. You'll notice this line is red. Again, I can click on that, change the color, make it dotted or dashed, and you can see it's right on top of the table because they are equivalent. So I can add an equation here. I might also want to add just a simple point. So if I want to choose a point on the line, let's say I'm going to choose 2, 4, I could put in that point. It gives me an option to label it. And now I can see that that is a point on this line, or a solution, or a part of this function. So I'm going to be using some Desmos graphs to check and verify some of our work this week. So I just wanted to show you how it works. You can come over here to the little tool. I know my screen is hiding part of it, but you can see you can put as many grid lines as you want, take those off. You can add labels to your axes if you want to get that fancy. But just in case you were wondering where my graphs were coming from this week, this is where I got them. So our first problem is Franklin's faucet that was leaking. So he put a bucket underneath to catch the water. After a while, Franklin started keeping track of how much water was in the bucket. His data is in the table below. Is the relationship linear or nonlinear? Write an equation for the relationship and predict how much water will be in the bucket after 14 hours if Franklin doesn't stop the leak. So on my paper, I started by recording the table. And I wanted to think about, do the quarts of water increase at a constant rate? So pause the video if you can and figure out if the quarts of water increase at a constant rate. And I noticed that as the hours increase by 1 hour, the number of quarts in the bucket increases by 1.5. And each time the difference is 1.5. So to go from 8 to 9.5 is 1.5. And I can't simply add that to get to the 14th term. I need to figure out what it is. But because it increases at a constant rate, it is a linear relationship. So the first answer to the question is yes. So to figure out the equation, I'm going to start with y equals mx plus b. And remember that m represents the rate of change or the slope. So that's the first thing that we're going to figure out. And then b is going to represent the initial value or the starting point. So those are the pieces of our equation that we are going to figure out in this problem. So the first thing we need to do is look at our x and y values and determine how we can use those to figure out the pieces of the equation that are unknown. So starting with the slope, we're going to take the change in y over the change in x. And I'm just going to pick two terms from the table. Make sure you keep them in the same order. So I'm going to start with 6.5 minus 5, and then 3 minus 2. So two y values over two x values, and the difference there is 1.5 over 1. So the rate of change is 1.5. We already knew that. So we're just verifying and going over one way that we could use the equations that we've learned to verify what we see in the table. So now the part of my equation that I have is y equals 1.5x plus b. So to get that starting value, I need to go back and figure out, using two of those points, and I'm going to use 2, 5, to figure out what my b value is by plugging in the x and the y that I got from the table. Again, you can choose any x, y value, you'll get the same answer. So I plug in 5 for y and 2 for x and solve, I end up with 5 equals 3 plus b. Now I know 3 plus 2 is 5, so b has to equal 2, and that's the starting value in my equation. So now to write my equation, I just need to figure out or go back and write those values in to y equals mx plus b form. So my slope was 1.5, so I have y equals 1.5 or 1.5 x plus my initial value 2. So the equation for this line is 1.5x plus 2. Now I can go back and use that equation to figure out the 14th hour by plugging in 14 for x. So this time I'm going to have y equals 1.5 times 14 plus 2. And that's just a simple equation. So I'm going to take 1.5 times 14 plus 2. If I don't have a calculator, I know 1 times 14 is 14, and half of 14 is 7. 14 plus 7 is 21. 21 plus 2 is 23. So that is the amount of water in the bucket after 14 hours. So if I want to verify this with a graph, I can come over here to Desmos, and you can see here that I've put this table of values in, the equation that we created, and I can look at the line. You can see all of the points here from my table that are already on the graph, and I can look at where the x value is 14 and know that the y value is 23, so that verifies all the work that we did. Our second problem is Eli's distance from home as he rides his bike at a steady rate. So the word steady rate tells me that this is constant. We're going to find the slope and the y-intercept and figure out how fast Eli rides his bike in miles per hour. So that's going to be our unit rate. And write an equation in y equals mx plus b form that represents the miles, y, that Eli goes in x hours. So again, on my paper, I set up the table, and I'm going to look at how to find the slope, which again is your change in y over your change in x. I'm going to choose 2 points from the table, or 2 xy values, starting with 26 minus 14 and 2 minus 1, which gives me 12 over 1. And you might notice from the table that each time that is increasing by, let me turn that down, by 12, so that the miles are increasing at a steady rate of 12 miles. So now I'm going to go in and write my equation, y equals mx plus b form, starting with my slope, now that I know is 12. And I'm going to start with 12x plus b. To figure out b, I just need to choose 2 xy value, or 1 xy value, 2 points, or 2 coordinates, getting my words mixed up. And I'm going to say time is x, distance is y. I can choose any of those, so I'm going to pick the easiest one. And I'm going to use 114. So if 14 is y and x is 1, I get 14 equals 12 plus b. So that means 14, all I have to do to isolate that variable is subtract 12 from both sides. You might be able to do this mentally, but just to review, so b equals 2. And that's my initial value, or my starting point. So now I just need to plug those variables into y equals mx plus b form. I get y equals 12x plus 2. Now, to get how fast he rides in miles per hour, I just need to find that unit rate. And the table tells me at 1 hour, I've gone 14 miles. The rate is constant, so I know that that is my unit rate, that he's riding 14 miles per hour. Number 3 is a pool in the shape of a rectangular prism. On Monday, water was pumped out of the pool at a constant rate, starting at 12 p.m. At 12:15 p.m., the water in the pool was 45 inches deep. At 12:35 p.m., the water in the pool was 41 inches deep. So first, by how many inches does the depth of the water decrease each minute? And number 2, write an equation that represents y, the depth of the water in inches, after x minutes. So this is a problem where we're going to really have to interpret what the information is. So thinking about setting up a table, I started with 12 o'clock, 12:15, and 12:35, the information that was given in the problem, and I added the depth at 12:15 and the depth at 12:35 to my table. So pause for a minute and think about how many inches per minute. That would be your rate, your unit rate, or your slope. How might you figure that out? There are actually 2 ways that you could figure this out, and I'm going to show both ways because both of them will work. So what I did in my table is I looked at the times and I tried to give those, because if you look at the time, it's kind of hard to use those as an x value on a graph. So since we started at 12 o'clock, I made that my 0. And then 15 minutes went by and 35 minutes went by. So I put in -15 and -35 because that time has gone away. So now I have to figure out how many inches per minute. Well, I could simply do unit rate. I know that from 45 minutes to 41 minutes, that was a difference of 4 minutes, or 4 inches, I'm sorry. And on the top, from 12:15 to 12:35, that was 20 minutes. So the pool lost 4 inches in 20 minutes. I can use that ratio to determine a unit rate by figuring out how many inches in 1 minute. So if I set up those 2 ratios equivalent to each other, all I need to do to figure out 1 minute is to do 4 divided by 20, and that gives me 2/10 of an inch per minute, or 0.2. That's one way that you could have figured out the unit rate, or how many inches the depth of the water decreases each minute. The other way I could do it is using y equals mx plus b, or determining the slope. So the change in y over the change in x. Again, I can't just use the times, I need to use the values of the times since the starting point. So I did 45 minus 41 as my y values, and then I can take the difference of those two times, negative 15 minus negative 35, to get my difference in x values. And I get the same thing, I get 4 over 20, or 1/5. Now, you might think, but 1/5 is a different answer than 2/10. While they might look different, one's in decimal form and one's in fraction, 1/5 is equivalent to 2/10 as a fraction. And you could use either one. But sometimes when we're trying to work some mathematical problems, for me, it's easier to use decimal form. Both are correct, but you could choose which one you want to use, and I'm going to use the decimal form. So now that I know my slope or my rate of change, I'm going to use both strategies to figure out the initial value because both will work. If you have the chance to pause and think about how you might figure out the initial value or the depth of the pool at noon, at the starting time 0. Now your first instinct might be to subtract 4 minutes, but if I go back 4 minutes, I have to go back, 4 inches, I have to go back 20 minutes, and that would give me a starting time of 11:55. So I thought about 12 o'clock was 15 minutes ago. If I know that I'm losing 2/10 of an inch per minute, I can just multiply 2/10 times 15, and that gives me 3. So from 12 o'clock to 12:15, the pool lost 3 inches, not 4 inches. So you'll notice the times aren't really increasing at a constant rate on my table, so I can't just go back 4 inches. I need to figure out how many inches happened in 15 minutes, not 20. So 3 inches. So the pool's value started at 48 inches. I could also use my equation, just like we've been doing, to figure out that initial value. So if y is 45, my slope is 2/10, and at that point in time, I would use negative 15 for my time because I had lost 15 minutes at 12:15. So I can use those two values, that negative 15:45 from the table. You could use the other two, and that would give you the same answer. And now I can just solve this equation. 45 equals negative 3 plus b. To isolate b, I'm going to add 3 to both sides, and b equals 48. That means that my starting value was 48 inches. And now all I have to do is go back and plug those in for number 2 to write the equation y equals 2/10 x plus 48, or my initial value. If you want to use the fraction, that would work as well. Y equals, we're going to do 1/5 x plus 48. And that is the same equation, just depending on how you want to interpret your fractions. In a graph, I can verify this. If I know this is my equation and this is my table of values, I can look at my graph and see right here where the line crosses the y-axis is going to give me my initial value, or my y-intercept. So I know that that is correct. Part D, Billy is training for a long-distance running event. During one training session, he records the miles run after every 5 minutes. So the table shows the values. He notices the table shows a linear relationship. What is the rate of change for the table? And then we're going to complete the sentence. This means Billy runs what for each what. So the first thing before you continue is to look at the table and determine what patterns you notice. Now, you might notice that the table is increasing, or the y values are increasing by a constant rate. So each time it's increasing by 625 thousandths. Seems like a silly number to be working with, but if any of you run track or swim, you know sometimes that 1,000th of a second or a mile could really make a difference in who wins. Now, the rate is not 625 thousandths because the time in minutes is increasing by 5 minutes each time, not just 1 minute. So we do know that it's a linear relationship because it is increasing at a constant rate. but we really need to figure out what is that relationship between x and y. That's the linear relationship. So I can simply divide y by x or find the unit rate. So if I take 625 thousandths divided by 5, I get 125 thousandths. So that is the relationship, and that tells me the miles run per minute. So to complete the sentence, this tells me that Billy runs 125 thousandths of a mile every minute, or for each minute. For our last problem this week, we're going to look at a newspaper. For $1,200, a business can post an advertisement for 30 days. For $1,500, the advertisement will be posted for 60 days. The relationship pairing cost to days is linear, so we know it increases at a constant rate. We're going to write a function that can be used to model the relationship between the cost, y, and the number of days, x, that an advertisement will be posted. So again, I set up my table, and you may have noticed that the first few tables that we used were done horizontally, and the last two are vertically. It doesn't matter which way you set up your table. It's really a matter of what's easiest for you to interpret. So if you chose to do yours horizontally, that's fine. I just wanted to show both in my video so you could see how that works. So if I know my x and y values are 30 and 1200 or 60 and 1500, I can use that ordered pair to solve y, or to find the missing terms in y equals mx plus b like we've been doing all along. Change in y over change in x. So I can take two y values, 1500 minus 1200, and two x values. I'm going to use 60 and 30, and that gives me 300 over 30. So that means $300 every 30 days. But now, if you look at the table, it says 30 days is $1,200. So when I convert that or simplify that to unit rate, I get 10 over 1. That means I'm paying $10 per day. But there's something there that's an initial value. So that's making me think, if I were to interpret this, that there's an upfront cost to run an advertisement in this newspaper. So I need to figure out what that is. So I can plug in some values to the equation. I know the slope or the rate of change is $10 per day, and I'm just going to go back and plug in two values for x and y. So I'm going to let my x value be 30 and my y value be 1200. So 1200 equals 10 times 30 plus the starting value. Now all I have to do now is solve the equation. 1200 equals 300 plus b. 300 plus what is 1200? I could subtract 300 from both sides or use mental math to know that b, or the initial value, is 900. So what that means is, to run an advertisement in this paper, I have to pay an upfront cost of $900. So no matter what, at day 0, I've already paid $900. And then for every 30 days, I'm going to pay an additional $300, or it's the same as $10 a day. So then the function would be y equals 10x plus 900. And that would be the answer to the question. Again, if I want to go back and look at a graph, I can see it here where I've put the table of values in. I went ahead and put in that starting value now that I found it, because now I can see that's my y-intercept, and that's where it starts. So here is your final challenge, your final pattern, your last function. And we have a pattern with 3 squares, and you can see it increases in a stair-step pattern. And at the bottom, squares in step 43 is 990. So your challenge this week is to figure out the expression that would tell us how many squares are in the nth pattern. If you like these patterns and you'd like some more, go to visualpatterns.org. There's a ton of them there. And thank you for tuning in. I hope you have a wonderful rest of your week, and I really look forward to seeing some of you back in school. And take good care. Bye-bye.